There's a way to measure equilibrium, and it's called the equilibrium constant. Now, if we were to take any equation, and we took the coefficient in front of the formula, coefficient in front of the formula, these are the reactants. It's a reversible reaction. Coefficient product, coefficient product. Generally speaking, we would say a value called Kc. Now, Kc is called the equilibrium constant, and it gives us a measure of where the equilibrium lies. Are the reactants being favoured? In other words, does it lie to the left where we form hardly any products, or does it lie to the right where we form lots of products and the forward reaction is favoured? So Kc is basically the concentration of the products over the concentration of the reactants. And it's not just as simple as that, obviously. What you need to do is you need to take the product formula, raise it to the power of the coefficient, multiply. This is not an add sign. Even though that's an add sign, this is not an add sign. Multiply the other product and raise it to its coefficient. Same is true for the reactants. You take the reactants and you raise them to their coefficients. With the equilibrium constant, you only use aqueous solutions and gases. Solids and liquids are left out of the equilibrium constant. When Kc has got a high value, and by a high value we mean greater than 1, there would be proportionally more of the substance on the right. Why? Because it's products over reactants. So if I have more products, I will land up, concentration, if we're more specific, if I have more product, then I will land up with a big number, bigger than 1. If I have more reactant, so in other words we're favouring the reverse reaction, then I would have a Kc value less than 1. So when Kc has a high value, there will be proportionally more of the substance on the right, in other words more product. We say that the equilibrium lies to the right. Obviously, the opposite is true of a low value. Only temperature alters the Kc value for a specific reaction. Otherwise, the Kc value stays absolutely constant the whole time. It is called the equilibrium constant after all. Solids and pure liquids are always left out of Kc calculations. So, if I had a reaction of hydrogen plus iodine gives me hydrogen iodide, I would say product, hydrogen iodide, raised to the power of the coefficient, the concentration of the reactant. These square brackets mean concentration of. Concentration of hydrogen, there is a 1 in front, so raised to imaginary 1. And concentration of iodine, these are multiplied together. And again, I've got an invisible 1 there, so I'll put an invisible 1 there. The square bracket around the H2 means the concentration of hydrogen gas. The square bracket, the concentration of hydrogen iodide gas. The square bracket, the concentration of iodine gas. As we increase the temperature, we always favour an endothermic reaction. So, if we were to take this particular reaction over here, in the last video we learned that this was an exothermic reaction, and you have got if you're going to increase the temperature, you'll favour the endothermic, which means you will favour the reverse reaction. In other words, I'll get a lot more of that. The concentration will increase of the reactants, and therefore Kc will get smaller. If the temperature changes, a new equilibrium with a different Kc will be established. Let's take a look at this graph. I want you to look very carefully at this graph. The axis says number of moles. We've previously looked at a graph where the axis said the rate of the reaction. This time it is number of moles times time. And this time, all that we need for equilibrium is where the number of moles is staying constant. That means it has reached an equilibrium position. So there are 2 equilibrium positions in this story. The other thing is that I've got x here and I've got x2, y3. X started at 4 and decreased. whilst x2, y3 started at 0 and increase. This is the concentration of each of these, or the number of moles in solution. Over here, my x increased whilst my x2, y3 decreased. And over here, there was this sudden increase in x, which means I probably added some x in there because it's very sudden. And then it slowly decreases, so it is probably going to tell me a story around that. So if I take this as a little balanced equation over here, we can see that initially I was getting rid of this reactant and making lots of the product. So I favored the forward reaction. Equilibrium got established. Something happened at 60 seconds to favor the reverse reaction. Then after that, it established a new equilibrium. At 150 seconds, I obviously added some x to the solution, and that then favored the forward reaction, and the x2, y3 went up. Now, there's no such stuff as any of that. There's no x's, there's no y's, there's no x2, y3. These are fictitious elements just to illustrate some equilibrium principles, and they do this in exams. So, gases x and y are pumped into a 2,5 decimeter cube container. When the container was sealed, at 4 moles of gas x and 4 moles of gas y were present, the following equilibrium was established. Using the graph, determine the Kc value at 50 seconds. So, if we look back at that graph, first let's get the Kc formula. It's going to be products raised to the imaginary 1, reactants raised to 2, raised to 3. And we do not add them or anything. We multiply everything and divide. They are all gases, so we can include them all in Kc. What did I start with? I started with 4, 4, and 0. Then if you look at the graph, you make 0,5 moles of this product. Now remember that there is a mole ratio that tells you that 2 x's plus 3 y's gives you 1 of x2, y3. So there is a link somehow between those, what you use of the reactant and what you make of the product. I don't know what I used of the reactant. I only know what I made of the product. I then can use a mole ratio of 2 is to 3 is to 1. So I simply take 1, 0,5, multiplied by 3, and multiplied by 2 to get those two values over there. I started with 4, I used 1, I'm left with 3. I started with 4, I used 1,5, I'm left with 2,5. So at the end of equilibrium, I have got a volume that told me I just had a volume of 2,5 decimeters cubed, so it's the same for all the gases. And I can work out a concentration for each of these different gases. Then I substitute the concentrations in 4x, 4y, and 4x2y3. I then calculate my Kc value by just punching it into the calculator. Kc does not have a unit at all.